should be able to do this, to do the graph. You should be able to understand what the probabilities are doing. That's what I find the most important, is that you make sense out of this. Like yesterday when we compared a probability that was like 16% versus 46%, where were your larger numbers, your larger probabilities? If you have a better chance, a chance of success, you should have more people being successful, more successes than failures, right? If your percentage of success is higher. And that's what you want, more successes, your percents are higher. So the middle of the road, and we'll see where this one brings us. So the survey in example 5 found that 53% of the men believe, I think this is women, sorry. The women believe that there is a link between playing violent video games and teens exhibiting violent behavior. You randomly select, oh, maybe this is men. US women. Okay, so this is men, they changed men. Okay. They did theirs and found 53% of the men believe there is a link versus the women one. All right, so you randomly select 5 men and you ask them whether they believe there is a link between playing violent video games and teens exhibiting violent behavior. And again, this is just like we did yesterday. Just like we did yesterday with the women believing this. So let's pull apart, let's talk the whole thing. What makes this a probability distribution? For what? Binomial. So step back, one step back, just what makes this a table that works. What makes our table a probability distribution? Not binomial. That's binomial. Before that, what makes that probability thing work? When we put everything on the table, what do our probabilities look like? Where do they fall between? 0 and 1. And what's the second criteria? When we add up all the probabilities, the sum is equal to 1. This makes it a probability distribution. What makes this a binomial probability distribution? Now, Devin, how many choices do you get? 2 choices, 2 outcomes. What else? The probability has to be consistent. Probabilities are fixed. These are independent. You're going to do this for n amount of trials. And your random variable gives you the possible outcomes. 2 possibilities, 2 possible outcomes, a success, a failure. If they give us a whole slew of them, that's okay, as long as when we ask that question, we ask a question that gives them a yay, nay situation. Okay, gross. All right, so now we're going to start this. Lay these out. N, P, Q, X. What's N in this situation? 5. What's my probability of success? Probability that this man believes that there is a link. 53%. What's Q? Not 57. 47. 1 minus 53. And X is my variable. That's going to represent all their outcomes, all their possible results. 0 could not believe, could say, you could have nobody that says that. 1 person, 2 people, and so forth. So this is going to go from 0 to 5. Okay. Now I know this is binomial. If my probabilities were going to change between from one to the next, God bless you, then this is not a binomial. Okay. So the first thing we need to do is complete our table. This is our probability distribution table. So we're going to complete our table. So whether you use Bernoulli's, you're always going to measure your successes first, and then your failures, and you're going to keep changing this, this, this. Or binomial PDF. If you have to string them out, remember they're in alphabetical order. N, 5, P, and start with the 0. This is exactly what you get when you're prompted and then you paste. It's exactly what you get. And then you're just going to alternate through here. Change that from 0 to 1 to 2 to 3 to 4 to 5. Isn't that easier than the C? But I think for you guys, it actually makes more sense, right? You kind of get the concept of this. So take a minute, fill those in. Okay, so hopefully you got these answers. Remember, I want 3 decimal places. Be careful when you get the E. The E means you're going to have to move your decimal. No probability can be greater than 1. And it can't even be equal to 1 if you have a chart like this. Because the sum cannot be greater than 1. So my sum is greater than 1. This is what makes it a probability distribution. My sum is greater than 1, and my probabilities are between 0 and 1. This is a 4. Looks a little bit strange. Okay. Now, we can answer these questions right off of this. What is the probability that exactly 2 of them responded yes? 0.292. Thank you. What is the probability that at least 2 responded yes? What would I do for at least 2?
0, 1, 2. Oh wait, no.
2? Good. 2, 3, 4, 5. When you say at least, that's the least it could be. If I have at least $2 in my pocket, and we go shopping, and you say, can I borrow $2? You say, yeah, I have at least $2. So I have $2 or more, so I can definitely give you $2. You're going to add these pieces up. Okay, so if you add them all up, 8, 4, 8. Now the last one says fewer than 2. What is fewer than 2? 0 and 1. Can I count 2? No, I need to be fewer than 2. So all I have to do is add these 2 guys up, or I can use my complement piece. Good. You subtract this guy from 1, and you still get the same answer. Now, yesterday we kind of took a look at where are your large numbers. Your large numbers are falling smack in the middle, aren't they? Here's your pretty large numbers right in there. Why? It's a normal curve. What makes it a normal curve?
Survey is about 50%.
Ah, it's about 50%. It's about half and half, right? Look where my percentage is. My percent, very good, Sarah. Your percentage is smack in the middle. So it should be a normal thing. You have a 50-50 chance almost here. So when we graph this guy, we're going to graph this like we graphed before. Our x values are going to be our outcomes. Our y values are going to be our frequencies, but in this case, our probabilities, kind of like what we did before. And we're going to start with these guys. You're just going to graph them by your bars. Okay. Okay, and make sure you're able to graph. You're going to go from 0 to the highest is, say, 35 cents. So go by 5 cents. Give me a title up here. Just make sure I get a title. And just make your bars. So the first one is 0.02. That is below 0.05. Then the second one is 0.129, so a little bit above the 10, a little close to the 13, and close to the 30 cents, a little bit higher, close to 30, little over the 30, 185, almost under the 20, and then the last guy, less than 5. See our normal curve? Pretty much have a normal curve here. Okay? And that is because, like Sarah said, our probability is very close to the halfway mark, the 50-50. Now, yesterday we looked at one that had a very small probability. It had 16%. So if you think about 16%, is it a strong possibility? If the probability that they say yes is 16%, do you expect more people to say yes or less people to say yes? Less people to say yes. So my higher numbers now are going to be up here. Okay? And I'm going to be skewed. I'm not going to have as many down here. I don't expect them to say yes. It kind of has a little bit of a backwards approach here. Yes?
Can you show me how you put in your calculator?
Sure. Sure. Go second pairs. Second pairs. And come down till you see the word binomial. And there's two of them, binomial PDF, binomial CDF. We want the PDF, probability distribution function. So we come here, and it prompts you. Do you have this on yours with the prompt? Okay. So you're going to put in 5. You're going to say your probability is 0.53. We always measure our successes. And we're just going to start it at the 0. And then you paste. So when you hit this, it'll give you your probability. Then all you have to do, John, second enter, and just change that 0 to a 1 all the way through your table. Makes life a lot easier than the C. If you do the C, you then have to come back and change this to a 1, this to a 4. Then you got to change this to a 2, this to a 3. You have to change it in 3 places. But it makes it a little bit easier. And back in Algebra 2, when you had an at least, you had to string them all out. The 501, the 502, the 503, the 504. You had to add them all up in between. Now we just take them right off the table. I think this is much easier. Okay. So just to talk about the graphs for a second. All right. Just to talk about these graphs for a second. When we had a probability of 0.16, we said, we noticed that 0.16, you're not going to get a lot of people saying yes, right? So do I expect big numbers down here for 4 out of 4 people to say yes? I expect this to be small, don't I? I expect this one to be a little higher. This one to be a little higher. I expect it to look like this. If my probability is very small, I don't expect everybody to say yes. Right? So this is skewed to the right. These are on your notes on the very bottom of the first page. When your probability is less than 0.5, then your distribution is skewed to the right. It's kind of the opposite of what you would think. Because the negative is pointing that way, your graph is skewed to the right. You're not going to get a lot of people saying yes. Yes. Hi, how are you? Yes, he is. Do you want to talk to him, or do you want me to send him down next period? Yeah. Yeah, of course not. Hold on. Stephen? It's Mr. Iolano. I say wait, I have to wake Stephen up. He's on the phone. He's on the phone. Okay. When it was close, like the 0.53, we noticed that we had a normal curve. Kind of a normal curve here. Okay? Because everything was middle of the road. And that's where I expect my numbers to be. When we had the situation where it was very high, I think we did a 0.86, then, like the operations, don't I expect a lot of them to be successful? They might say these were the operations. Remember when we looked at the operations? We said they had an 85% chance of being successful. Then shouldn't more of them work? Shouldn't more of them be successful? So my bigger bars are going to be up over here by these numbers. My small, I don't want these to happen, right? I don't want them to have 0 successes. So now this is skewed left. We call this normal or symmetric. Okay. So when you think about these, think about a real life situation. Think about the operations. If I'm a doctor and I'm operating on 10 patients, don't I want a lot of successes? Yeah, I sure do. So my success rate should be good, or I shouldn't be operating, first of all. And I should get most of these here being good. I should get very little that are not good. So that's where your skew comes in. Okay? This good with you guys? Okay, good. Okay, now, the last thing too is finding the mean and the standard deviations. You can find the mean and the standard deviation off of any of these. So let's do one more. We're gonna do example 7. Hang on. Let's try 7. Okay. What page is it on? Page 208. Okay. A recent study showed that 19% of people ages 16 and older own an e-reader. You randomly select 4 people ages 16 and older, and you ask them if they own an e-reader. Is an e-reader like a Nook? Is that what they're?
Yeah.
Okay, but all your phones and everything else can be readers, right?
Yeah, but it's like it's not the same.
This is a special. I have a Nook. I do have a Nook, but all right. So now, let's talk about this. Let's find our pieces and see if, in fact, this is a binomial. Which n? How many people are you asking? 4. What's the probability that they say yes, that they own an e-reader? 0.19, pretty small, right? What's the probability that they don't own an e-reader?
81.
Good, 81. And my x is going to go from 0 to 4. Oh, missing a line. Who did this? All right, so now, is this binomial?
Yeah.
Yes, this is binomial. Okay, binomial because we did it n amount of trials, n amount of trials, n amount of times, 4 in this case. Probability stays fixed. We give them 2 choices, e-reader or not e-reader. And my x variable goes from 0 to 4. Okay, I measure the answers of success that we have. So again, you're going to put it in your binomial PDF. Are most of you using the binomial PDF, or are you using safe? Yeah, but binomial. This is so much easier. You can just even pull an old one down and not hit enter. and just go through and change. It likes to do this on me. Okay, just go through and change this. 4, change this to 16, 19, change this to 0. Okay. All right. Boy, this is high. Did we expect this to be high? Yeah, because the probability that they're going to say yes is pretty small, right? So it kind of works in reverse. When you get down to the bottom, I bet you we get it. Why is this doing this? Okay. All right, 403. Now watch. If these guys have to add up to 1, the rest of them have to be pretty small, don't they? I'm sure you're going to get a lot of E's in here. Ladies. You got some E's? Not yet. Next one has an E?
No, E's. I didn't get E's.
You didn't get any? Oh, okay. How many decimal places do we round to? 3. Oh, whoa, no E's. Almost. Okay, so where's the skew? Where's the skew for this guy? Skew to the right. So if we made this graph again, and we did the graph, we would see the larger ones over here, then it would go down a little bit, go down a lot, go down, and way down. So this is skewed to the right. And again, we didn't expect a lot of people to say yes if the probability that they will say yes is so small. Okay? So we can see all that in there, which is good that we did one again because we did it yesterday. Now, because this is a distribution table, just like your frequency table, you can do L1, L2. And you can do 1 var, stat, L1, L2, and you can find the mean, you can find the standard deviation, and we can square that, and we can find the variance. The only thing you won't be able to find in this is your sample standard deviation, because the sum of your frequencies, which is our probabilities, is equal to 1. So a sample says n minus 1, not happening. So try this. Put this in your calculator and try this and see if we can find the mean, the population standard deviation, and then give me the variance. This is your variance. Go to the statistics part and square it for me. I'm counting on you guys because I don't have this. Anybody come up with the mean? 0.759. Okay. Standard deviation?
0.732.
Okay. And variance? Okay. Go to stat. Go to that stat to var statistics and square your variance. What does this mean? My mean is 0.759. Where does that fall? Not in my probabilities, but where does that fall? Right in here. On the average, I'm going to get either no people or one person, somewhere between there. I can't have a fractional person, person say yes, but it's somewhere in between there. Those are where my highest numbers are. My mean has to fall there, doesn't it? And if you square this in your calc, what do you get for this? Did you do it, Chris? Okay, we're good for that. Now, you also have a set of equations. That's on your formula sheet as well. And it gives you the mean, and it gives you the variance, and it gives you the standard deviation. To find the mean, n times p. To find the variance, n times p times q. And to find the standard deviation, it's the square root of this. Why would we use this instead of L1, L2? Well, L1, L2 works great here. You only had 5 entries. You don't want to do a table with 100 entries and stick that into your calculator to find the mean. But I just want to show you that these formulas work. So we're going to practice on this. To find the mean, we're going to take n, which we laid out already, 4 times my probability, 0.19. When I multiply that, that gives me 0.76. Pretty darn close, right? Rounded. Okay? When I do my variance, I already have my n times p, so all I have to do is 0.76 times my q, 0.81. And that should give me darn close to my 782. Nope, to my 620, sorry. And then, for this guy, I'm going to take whatever this thing was and square root it. And that will give me my 0.782. Okay. So I want to show you that these formulas work before we actually go to use them. Table is small, L1, L2 works wonderfully. Table is a little bit bigger, and I don't want to go through putting that whole thing in my calculator, nor do I want to make a table for it. I use these. So do we agree that they work?
Yes.
Okay, so why would I need to use these? Because sometimes you're going to get a problem that looks like this. And it says, in Pittsburgh, Pennsylvania, about 56% of the days a year are cloudy. Find the mean, the variance, and the standard deviation for the number of cloudy days in June. So I could absolutely make a table, right? What's my n? 30. 30 days in June. Good. What's my p?
3.56.
What's my q? And my x is going to have to go from 0 to 30. So I could absolutely make a table from 0 all the way to 30. Would you really want to do that? Just to find me? Because then once you work all those parts out, you have to put this in your L1, your L2.
So you're bound to mess up somewhere.
Probably, with all those weird numbers in there. The nice part, what kind of curve will this be? Olivia, what kind of curve will this come out to be if I graph this?
Regular.
The regular. Good. It would be symmetric because my probability is fairly in the middle, right? So we know that part of it. Now, I could absolutely do that if I wanted to, or I could use my new formulas. Because all I want to know is the mean, the variance, and the standard deviation. I didn't ask for any probabilities. If I asked for probabilities, yeah, then I'd have to do my chart. But if I only want the mean, we know that these work because we saw them work. So n, which is 30, and p, which is 0.56. So this comes out to be 16.8. What does that represent, 16.8?
Percent of days. What?
The number of days that we have cloudy. On the average, the number of cloudy days is 16.8. Now think about this for a second. If your probability is close to 50%, what is 50% of 30? 15. Shouldn't I be around 15 somewhere? Shouldn't I be a little higher because I'm a little higher than 50%? Isn't that what I'm basically doing? Taking 56% of 30? That's exactly what I'm doing.
So would you have to round that number to a whole number since you only have...
Since it's days, I would leave this with a decimal. I would leave this with one decimal because your days are the x values are whole numbers. Your mean always has one more decimal. Remember how we do the means? It's
just
always
thought-
one more decimal than your x value.
just thought that's part of the,
Right, but like we can't really have part of a person either, but we still always round one more than the x value. Just like the average amount of kids, 2.3.
do we remember those formulas?
No, I'll give you those formulas. I will give you those formulas. To find your standard deviation, your variance squared, this is our variance. We do n times k, so we're doing this times k. If you want, you already did this part. But doesn't your mean make sense? Your mean is just your average. So if I was 56% of my 30, that makes absolute sense. So when you do this, your variance will be 7.4. To find your standard deviation, all you have to do is take the square root of that guy. Because if you're only going to get the mean and the standard deviation out of this, no sense making a table of 30. And we saw that it worked. When we did a small table, we saw that it worked, so we know that it'll work for this one. Okay. You guys try 8. San Francisco, California has 44% of days in a year that are clear. Find the mean, the variance, and the standard deviation for the month of May. For the
31.
Yeah.
31. You gotta lay your N and your P and your Q out. 31 days in May. Percent 44. Now, I would think, oh, it's the opposite of this. Will I get the same numbers? It's the same numbers that I used here. Will I get the same answers? No, because my P has changed. They add up to the same. Yep, they do, but they were reversed. Kind of like now I said they're clear, not cloudy. But in fact, 56% are cloudy. I didn't change that part, but I did ask what percentage is clear now. Even though they've got the same thing, I asked what percentage is clear. So my mean has to be 31 times 0.44. 13.64 days on the average will be clear in a month. Not a very big percentage, is it? No. The variance, you can just take this guy, 13.64, and multiply it by your Q. 0.56, and that's 7.6. And then your standard deviation, just take the square root of 7.6. And somewhere, I don't have that answer, like 2.7 or something like that. Somewhere around there. 2.76, something around there. 2.8, 2.7. I'll go with 2.8. Good? We talked about a lot in this little unit. We did a lot of